Hello, I am audible. Please just confirm. You can write in the chat box also if you are not able to speak. Please just confirm, so I'll start the session. Let me just. Okay, fine. Let us start. So actually, the today's session is about the topic is today. I'm going to take the week 8. This is so the topic is incompressible viscous flow in the pipe. So we are going to discuss about the pipe flow. We'll discuss question on laminar and turbulent flow and loss in the pipe, and another topic is the flow in non-circular conduit as well as the path multiple path pipe flow. So multiple path pipe flow means the series and the parallel connection, these kind of things. So actually we have discussed a lot about the question regarding this in the application of the Bernoullis, but here we are going to focus more specifically on the pipe flow. So as we have seen very uh, most of cases the actually liquid flow in the circular pipe, why it is not in the rectangular duct. So these are the things, these are the important points why the liquid not generally flow with the this rectangular duct. So these are the explanation is given because of the efficiency of the flow, minimize the friction losses. We are using minimize the friction losses. Due to this, we use this one. Prevent the uneven pressure gradient, because at the here at this the uneven pressure gradient, but as the circular the pressure gradient will be the equal. And so these are the and the distribution stress evenly throughout the surface, so less chance to burst. So these are the things. So and what is laminar flow and the turbulent flow? As you can see, here is the very smooth flow, and the parallel, the all the line is parallel to each other. But in the turbulent flow, as you can see, the zigzag flow is, that is the chaotic motion is happening in the turbulent flow region. So these are the some basic idea. And Reynolds number, what is Reynolds number? Is the ratio of inertia force divided by viscous force, and these are the expression rho v d by mu. D here is your characteristics length. D is a characteristics length. In case of the pipe flow, generally we consider characteristics length is d, diameter of the pipe. So as you know, the d is, we have discussed d is your characteristics length, or you can say the hydraulic diameter. So hydraulic diameter is nothing but 4 AC by P. For the circular pipe, if you will go for the circular pipe, A is what? A is the area of the circular pipe, pi by 4 into d square. So here you will put, if the pi by 4 into d square, pi d will be cancelled out. So your dh is equal to d. But how you will calculate the Reynolds number for the this is mu Reynolds number for the this type of duct using the dh value. You will calculate the dh value and put in them. But but interestingly, for the circular it is dh is equal to d. So that's why for in the circular pi we use Reynolds number rho v d by mu. So remember please, this is very very important. And the laminar flow is when the Reynolds number is less than or equal to 2300. Sometimes you will find in the book 2000, remember please. And your transition flow in between 2 2300 to 4000 and greater than 4000 equal to is the turbulent flow. Remember, these are things. And this is also very very important. So, and I have the lot of questions why I am discussing, because these are the some important points which you need to remember always if you are studying the pipe flow. So what is fully development region? So fully development region means when your velocity diagram, when your velocity distribution completely get the parabolic shape. Here you can see the parabolic shape is up to here, only up to here. Here is the, this is not parabolic. So once you will come at a distance, particular distance, your velocity distribution is completely parabolic. So after certain distance in the pipe flow, you will get the parabolic distribution. So up to that length, from initial to, from entrance to before developing the parabolic type of velocity profile, the length is the hydrodynamic entrance length, or you can say the fully developed length. So these are the things. So now let us move on the next topic, and how we will calculate the entrance length using the formula. This formula, and for the turbulent flow you will calculate this. Sometimes it is 10 times of the diameter. As a thumb rule you can consider. Now let us discuss about the question number 1. So the first question is the friction factor. The friction factor we are talking about here of laminar liquid flow in a circular pipe is proportional to friction factor. We are talking the Reynolds number inverse to the Reynolds number, square of the Reynolds number, or square root of the Reynolds number. So please, I need answer from your side. So you can write answer in the chat box. Which option will be correct? So I am waiting, please, as you will, as you have gone through the previous lectures what I have sir is taught in the NPTEL. So based on your understanding, you just please try to write your answer in the chat box. Which option is correct? Just you write A, B, C, D. Which one is correct? If you not know, I'll explain one by one. Okay, I'll wait 1 minute. After 1 minute, I'll discuss. Okay, if you not know, please you can write also no, don't know. So I'll discuss, because there is no meaning of the waiting in the lobby. Or I'll say one thing, you can also search on the Google also, because this question whatever I am solving here, this is for you only and for the NPTEL students. So because this is a practice one, so this is not your final thing. This will not consider in your final marks. So when I am solving, in asking any question, you can also search on the Google, and based on your answer, because when one will search on the Google, you will find out some clarification on that. You will remember for a long time. So please, if you don't know, first you try to by your understanding. If you not know, then you search on the Google and write answer here. And anyway, I'll discuss. Once you will search by your mobile or your laptop, so definitely you will remember for a long time. Okay, let us discuss. So we are talking about the friction factor. This is F for laminar and for turbulent. For laminar case, actually the friction factor F is equal to 64 by Re. This is the formula. So here you can see inversely proportional to Re. So the option B will be correct, inversely to the Reynolds number. B option will be correct. For turbulent flow, we'll discuss later. I have the question also. Question number 2. In asymptotically flow of viscous fluid, one of the following pairs of force strike a balance. Means when you will derive the asymptotically flow, so you have to balance two forces. Which forces? Means balance means here is, let us suppose, F1, F2. You have to balance two forces, and after balancing you will find out some relation. So which two forces? Whether inertia force and viscous force, pressure force, viscous force, gravity force, viscous force, inertia force, gravity force. So these are the options. So which option will be correct? Very important. So please just try to write your answer in the chat box. If you not know, you can write no. So I'll discuss one by one. Because why we waste time here? Because I have the lot of questions. So this is depend on your answer. How much we'll discuss the question today. So if you know, you just try to think, try to search. Not know, you can write just no. So I am waiting. So for this question, actually I have the detailed solution. So you have joined here, okay, fine, very good. But maybe some student not joined. So during the once I'll upload this video on YouTube, you can access. Okay, you are telling B, pressure and the viscous force. Okay, fine. Let us see. Yes, option B is correct. The pressure force and the viscous force, when you will equate, you will find out some relation between the pressure force and your viscous force, and this is uh, the relation whatever you will get known as the Hazen-Pauly flow of viscous. So what are the assumptions behind it? These are the assumptions. First, so let us read this one. What is written actually here? In Hazen-Pauly flow, steady laminar flow of viscous fluid through circular pipe at low Reynolds number. So remember please, this is about the laminar flow. The flow is derived by the pressure gradient. This is just general perspective. Then after the derivation is there. Since a steady, fully developed laminar flow, as I have discussed what they mean by fully developed, so you know already, and the inertial force are negligible, remember, and the resisting force is due to the viscous shear stress. Oh, these are the things. So here the assumption, just once you will go, the steady flow should be steady, means the flow parameters should not change with respect to time. Incompressible flow, that is density will be constant. Newtonian fluid, so means the constant density and viscosity mu. This is a Newtonian fluid, means tau is like that, du by dy. So this relation have. Another is the flow in a straight circular pipe, radius r, asymmetric fully developed flow, axial velocity u is equal to, that is the function of r, and function of r means what? As you can see here, this is the diameter and this is your radius, you know already. So as you know, the velocity change like that, means your velocity varying in the r direction. So that's why it is written. So, and the no slip condition, yes, and the body force, that is gravity, is negligible or small, act along the axis and include the pressure gradient if needed. So these are the assumptions. So I have the, based on the cylindrical coordinate I have the solutions, and based on your another way also I have, and very simple way, this is very simple way, very simple way I have. How? You just equate these two forces. As you have told, option B is correct, means the pressure gradient as well as your viscous force equate. So once you will equate these two things, what you will get? You just put tau is equal to mu du by dy, and the pressure gradient you will get, once you will put here at the place of tau, you will put what? Mu du by dy, because the Newtonian fluid we have assumed. So we will get these equations. We will get this, and after that you will integrate, and after integration you will get the final expression. This is your final expression. Once I'll upload this PPT or this PDF, you will go through. Then the pipe Hazen-Pawley equations is this. So remember please. And the volumetric flow is like that. Okay, let us move on the next question. Flow in pipe can be expected to be turbulent. The flow in pipe can be expected to be turbulent when Reynolds number based on mean velocity and pipe diameter is. Mean velocity means Reynolds number is rho u average into pipe diameter d divided by mu, dynamic viscosity. Based on this equation, when your fluid will be turbulent, when the Reynolds number will be 0, less than 2000, greater than 2000, greater than 3000, or greater than 100. So based on this option only, don't remember the whatever the final value. Here based on the option, which option may be correct, just try to understand. So again I am waiting for your answer. Question number 3. So hope you have got it, the previous one. Okay. So as we have seen already, your here you can see very clear. Yes. So actually when the flow is greater than Reynolds number have greater than 4000 in pipe flow, then we assume generally the turbulent flow. But in the question is given less than 2000 or greater than 2000. What is in the question? Less than or greater than? Question number 3. Yeah, less than 2000. Yes, in the less than 2000 it is laminar flow. greater than 100 and the greater than 3000. Greater than 100 means in it may be the 10,000, 1 lakh, something, whatever, and greater than 3000 also. So this option, actually the formation of option is not correct. So but we can go with the option C. Maybe the chance or the expected to be turbulent flow. So actually here should be the at least 4. So the option is not correct. So but if you will get such type of question, you will go with the option C. Remember please. Okay, question number 4. The question number 4, the the stresses that arise due to the fluctuation. Remember please, not friction, sorry. Due to the fluctuation in the velocity component in the turbulent flow are, whether it is Euler stresses, limit stresses, Reynolds stresses, principal stresses. So here little bit I'll discuss more. So first I want answer from your side, then I'll discuss. For question number 4, I'll give you, this is very important question. So you can search on Google also, and based on your, if you don't know, then search on Google and then you try to write your answer. So please just you try to write your answer. You have 2 minutes for this question because this is very important. Please try to write. Another 1 minute. Okay, option C you are telling, Reynolds stress. Okay, very good. Yes, option C will be correct, but how and what is this? So velocity fluctuation means when your flow is laminar, this is laminar I am writing. So if this is your velocity, not velocity, this axis is your representing the velocity and this is representing the time. Not sorry, this is representing the time and this is your velocity. So let us suppose you are measuring the velocity at a particular point using some instrument. You are measuring the velocity at a particular point using instrument. Let us suppose you are measuring here at point P1. So if the flow is laminar, you will get very smooth flow. There is no fluctuation in the flow. This is the laminar case. But once the flow will be turbulent, when the flow switch from laminar to turbulent, then the flow will be not like that. The flow will be, let me just delete, the flow will be like that. Sometimes high, low, high, low, high, low, like that. Means you will not get the exact value. Sometimes it will be, for the analysis, you cannot analyze this such type of velocity at a particular point. Someone asks you what will be the value of velocity at a particular point, how you will tell? Whether it is this amount, whether it is this amount, because here let us suppose here you have 2, here you have 1, here again you have the 2, -2. plus 2, 1. So which will be the correct? Whether here is the 1, 1.5. So in case of turbulent you cannot tell, but in case of laminar you can tell very easily because only one line, there is no fluctuation like that once you will measure. So what will happen? For the analysis of such turbulent flow, we'll draw a line. We take the average. Once you will take the average, maybe the value will, maybe the, if the fluctuation is more in the upper side, your average line will be shifted in the upper side and you will get something 1.5 or 1.4 thing. So here is flow is 1.4. Based on the fluctuation value, your this line will be shifted. And after that, here we are talking about the fluctuation due to the fluctuation in velocity. So let us suppose you have got the average line here. With this average line, your this much velocity is known as the fluctuation. This much velocity is known as the fluctuation. This will represent by u and this is represented by u dash. So you know already in the flow, actually we have the three-dimensional flow. One is streamwise, that is longitudinal, lateral flow and vertical flow. So similarly you will get corresponding u fluctuation, v fluctuation and w fluctuation. So Reynolds shear stress, based on these three fluctuation component, we got the Reynolds shear stress, which is your 9 component. So which is your 9 component? So u dash, u dash, u dash v dash and u dash w dash. Similarly the all things. So you know already, here is the v dash, u dash, v dash v dash and v dash w dash. Again w dash u dash and w dash v dash w dash w dash. So you will get such kind of things. So based on this, if you know the 6 component, you can calculate very easily, because u dash and v dash is equal to v dash u dash. So this is your Reynolds shear stress we will calculate generally. So based on these fluctuations, you get the Reynolds shear stress. So these are all the understanding behind this question. So let us move on the next one. Next one is the friction factor. The friction factor for a turbulent flow in smooth pipe varies. Turbulent flow, remember please, inversely as Reynolds number, directly as Reynolds number, as square of Reynolds number, inversely as 1 by 4th power of the Reynolds number. So you please just try to write your answer for this question. Hope you will got it, the concept of Reynolds stresses. Actually we tell the such stresses the Reynolds shear stresses, remember. So for this question, you just please try to write your answer in the chat box, question number 5. Okay, you are telling that T inversely as 1 by 4th power of Reynolds number. Okay, fine. Yes, it is inversely of the 1 by 4th of the Reynolds number. That's very very fine. 0.316 RE 1 by 4. Yes, okay, fine. Correct. So next question, question number 6, very very important. Eddy viscosity means, what do you mean by eddy viscosity? Option A, whether it is a physical property of the fluid, same as kinematic viscosity, always associated with laminar flow, and apparent viscosity due to the turbulent nature of the flow. Which one? Which one will be the correct? Right? Which option? Eddy viscosity. So you can just again you are telling option D, an apparent viscosity due to the turbulent nature of the flow. Yes, you are correct. This eddy viscosity, whatever I have discussed earlier, the turbulent flow, if this is your time and this is your velocity, we are discussing about streamwise. So turbulent flow will be like that, zigzag flow, not a constant value. So due to this turbulence, due to this motion, a viscosity generated. Because if the any things will be the zigzag motion, then the particle will collide and another friction will develop. Another friction will develop. That friction, because your fluid is having the friction due to this viscosity, but another friction you have due to the random motion of the fluid particle. So, and this random motion come from when the fluid will be the turbulent flow nature. So definitely it is the apparent viscosity. This is not a property of the fluid. This is not same as the kinematic, always associated with laminar never, because this is due to the fluctuation. So yes, fine. Now question number 7. Which of the following represent the major energy losses? Bend in the pipe fitting, sudden expansion, friction loss. Which of the following represent the major energy loss? Bend in the pipe fitting, sudden expansion, or the friction loss? So which option will be correct? So please just try to think. If you not know, you can also Google. Okay, maybe D you are telling. Yes, D is the correct. Because of the friction, there is a lot of loss in the pipe flow. Yes, correct. D option will be the correct. Okay, next question. Hydraulic gradient line is the sum of pressure head, datum head and kinetic head of the flowing fluid in a pipe. This statement is true, false, or cannot say. For question number 8. This is very important question. So please just try to write your answer, or if you not know, just you can search. Okay, you are telling the option B. So which will be the false? Yeah, this is not correct. Actually, the definition of energy gradient line is this: the sum of pressure head, datum head, and the kinetic head. How it look like? Let us draw a pipe and liquid is flowing. When we will inject a pipe, that is your piezometer, so you will get like here is the pressure, little bit lower here, little bit lower. So this will show you the your energy gradient, that is the hydraulic gradient line, which is pressure head plus datum head. Energy gradient line will be somewhere above because the addition of your kinetic head. Let us write the K. And why it is falling towards the flow? Because of the losses, because of the friction loss, you know already. So next one is, which of the following represent the loss of head at exit? Very important. At exit of the pipe. 0.5 v square by 2z, v square by 2z, 0.375 v square by 2z. Cannot say. Question number 9. So the question number 9 is, which of the following represent the loss of head at exit of the pipe? So please just try to write your answer. Because these are the loss estimation is very important, because it's directly affect the efficiency of the flow. Based on the loss, you will design your pump and all. Okay. So here your the final answer. Please just try to write your answer. If you not know, you just Google. Just Google whatever you will get the answer. You just write yes v square by 2z. That is fine.
Sir, this will be 0.5 skip e square by 2g, na, sir? Exit loss.
Dinesh, you are not audible. If you want to say something, you are not audible. Please.
Sir, this is A. Sir, I am audible, sir?
You are not audible. You just try to rejoin if you are trying to say
Okay.
something. Okay. The next question. For steady incompressible flow through a closed conduit of uniform cross section, the direction of the flow will be always from higher to lower elevation, from higher to lower pressure, from higher to lower velocity, from higher to lower piezometric head. For a steady incompressible flow, remember please, for a steady incompressible flow, this is very very important, flow through a closed conduit of uniform cross section, this is very very important also, the direction of flow will be always, which option will be correct? Very conceptual question actually. So you please just try to think on that. You have 2 minutes because this needs some attention. You need to some focus on the Bernoulli equation. So based on Bernoulli's equation, you definitely will get the final answer. So you have 2 minutes. Please just try to think and try to solve. Then you write your answer in the chat box. Remember one thing please, before applying any equation you have to know about the background of the equation, how what is how this whatever you will use the equation, the derivation you know, the assumption behind it know, then you just try to solve. But as for the Bernoulli's equation, here assumption is all regarding the Bernoulli's equation assumption, everything is fine here in for this question, because steady flow, yes, this was the assumption of the Bernoulli's incompressible uniform flow, but here is question is not uniform, the cross section uniform cross section you have, this is the trick for this question. So such type, this is actually the analytical type of question, so such type of question you can expect in the exam, competitive exam, gate exam, and other state exam, and your final exam also, NPTEL final exam. So I'm waiting, please just, you have another 1 minute. Okay, so let me discuss. So actually the question is, you have the uniform cross section of the pipe. So let us assume uniform cross section. This is a uniform cross section. Means that whatever the diameter here, the similar diameter throughout the pipe. Means whatever you have the velocity here, the similar velocity you will get here. Because continuity. Q is equal to, if this is A section, if this is B, QA is equal to QB. Area, velocity, area, velocity. If the area at both places same, the velocity will also same, because area is depend on pi by 4 into d square. So one thing is very clear, at point A and point P velocity will be the same. So you know one thing, the flow always from high pressure to or high energy to low energy. Whatever the flow you will see anywhere, high energy to low energy. Means at critical situations, what you will do, it should be the, that is high to low, you know already. Means the energy at A will be the greater than energy at B, and this, and how you will get the energy, based on the what, Bernoulli's equation, P by rho z plus V square by 2z plus Z. At point A, your energy should be greater than P by rho z plus V square by 2z plus Z. So one thing you know already, the velocity is same. If the velocity is same, velocity at A, velocity at B definitely will be cancel out. So it is depend on what, this P by rho g plus Z, P by rho g plus Z is what, your piezometric head, as we have discussed already here in this question. Here, what is piezometric head? That is pressure and your datum head, which represent the hydraulic gradient line, and energy gradient line is the combination of all three head, pressure head, datum head and kinetic head. So in such situation, your flow will be from higher to lower piezometric head. So this is very important. So this is some explanation. The velocity uniform because of the everything is thing. Okay, so now let us move with the question number 11. Question number 11 is very important. This is your numerical type question. Find a Darcy head loss due to the friction of, remember Darcy's head loss due to the friction in pipe of diameter 300 mm, length 50 meter, through which water is flowing at velocity 3 meter per second. Take the value of friction factor 0.01. Your friction factor is given 0.0124. Diameter of the pipe is 300 mm and the length of the pipe is 50 meter, and velocity is given 3 meter per second. So you need to calculate head loss. This is the data given. So please just try to calculate. And Darcy's head loss, so these head loss have the unique formula, because head loss you can calculate with a different way, but you need to calculate the Darcy's head loss. So for this question you have the 3 minutes, yes, within 3 minutes you can solve very easily. After that I'll discuss. Okay, you know the formula already. The HL is equal to, that is head loss. This is your FL V square by 2ZD. So here you need to put the values. 0.01, length is given 50 meter, velocity is 3 to 9.81, and your diameter of the pipe is 300 mm. So once you will write in meter, so 0.3 meter, and after the calculation you will get the final answer. So I'll just show you. Here is the, this is your final answer, 0.459. Oh no, this is your velocity head v square by 2z. So the final answer is this one, 0.7828. Yes, option A will be correct. So let me just cross check the calculation. It may be the wrong. You can also check. I am checking. You can also check. 0.0124. Here is a 0.0. Another 0 is 1024 into 50 into 9 and divided by 26. Yes, correct. 0.78. So now let us move on the next one. You can think like that also. The Darcy's formula is, I have written HL is equal to FLV square by 2ZD, but remember, friction factor into L by D ratio into your velocity head. Once you will combine, you will get this. So remember. Next one, a 2 kilometer long pipe of 0.2 meter diameter connect two reservoir. The difference between the water level in reservoir is 8 meter. The Darcy's Wisbach friction factor of the pipe is 0.04. According to the accounting for friction, entry and exit losses, the velocity in the pipe is, okay. So here the Darcy-Weisbach friction factor is given, but you need to calculate the friction due to the entry exit, and then after calculating these two, you need to calculate the velocity in the pipe. So I'm going to take the 5 minute break here. So if you want to take, you can also take. So I'll come back after 5 minutes. So if you not want to that break, then you can solve the question. Okay, let us discuss question number 12. So here you need to calculate the two losses. One is entry and another is exit. And already your Darcy's Weisbach friction factor is given 0.04. So actually you have to calculate the three losses. One is loss due to Darcy's Weisbach. Another one is your, that is total loss due to the entry, and another is due to the exit. So you have in the question 2 kilometer long pipe of diameter 2 connect two reservoir, and the, if let us suppose one reservoir is here, another is here. The water level is this much, and the difference between the water level is given already. The difference between the water level in the reservoir is 8 meter. The length is 2 kilometer, and the diameter of the pipe is 0.2 meter. So you need to calculate the velocity in the pipe. Here velocity. So how you will proceed? So here is your final the calculation I have. So actually the energy balance we will do. Energy balance means head loss, your, that is the head difference, is equal to head loss. Total head loss you can say. Total head loss means your head difference is 8 and the total head loss is FL V square by 2ZD, that is due to the friction, due to the entry and due to the exit. V square by 2Z and 0.5 V square by 2Z. So actually in the calculation here is considered the entry and exit. For entry and exit it is calculated by the, because you know already some here factor is in the calculation of your entry, some factor is required. Let us suppose here is the factor is k. Here also some factor, but sometime it is equal to 1. So it is equal to sometimes 1. So here is the, this is the proper way for the solving. So head loss, once we will have the V square by 2Z for the entry and some constant and some another constant for exit, V square by 2Z with some another constant like C2. So once we will take the add, then you will take, then another constant you will get, that is V square by 2Z, you can take the common and C1 plus C2 will be remain. So this will is written the here K total, that is the constant of both. So how you will calculate this constant? So the, for the calculation of the constant this is required. And yes, so you can take the Vf, that is V square by 2Z here, V square by 2Z here in the both, and after taking the final you will remain with the F L by D and plus K total. So you can think like that, and you 2z.8 will remain. Like the final expression will be v square by 2z. Here is your f L by d will be remain plus k total will be remain, and here is your delta h which is equal to 8 in the question is given. So when you will calculate v square, you will get what? 8 divided by into 2z will be here divided by f L by d plus k total. So once you will remove the here square, you will get the square root, and you know all the values already. So here is given what is the k exit and k totals. So in typically the entrance and exit loss coefficients for the pipe entering of discharge to large reservoir. So we generally take the k entry 0.5 and k exit is 1. Remember please. So that's why in case of exit I have written here v square by, initially I was written v square by 2z and it is something 0.5, 0.5 here, but for the this is the case of the reservoir, but maybe you will get some another. So for another system, the k, that is the this coefficient will be the different, remember always. So you know everything. So after that you will get the final expression is, after putting the value we will get the final answer 0.625, which is very important. 625 means you will go with the option A. This is one line calculation, but just for your understanding I have illustrated like that. One line means what? You will just write the difference FLV square by 2ZD plus V square by 2G plus 0.5 V square by 2Z. So you can get the V square by 2Z common. So FL by D will be remain, here is 1 plus 0.5. So V square by 2Z plus FLD by 1 plus 1.5, and here is the 8, and your final expression will be 2Z8 divided by 2Z8 FLD by 1.5. The similar process, and once you will remove square you will get root this side, and after calculation you will get 0.625, that is 0.623. Next one, very important, a water which having the unit weight 9.879 kilonewton meter cube, flow with a flow rate 0.3 meter cube per second through a pipe AB of 10 meter length and uniform cross section. Remember, uniform cross section. The end B is above end A. The pipe make an angle 30° to the horizontal. For a pressure of 12 kilonewton meter square at the end B, the corresponding pressure at A in kilonewton meter square. Please read the question very carefully and draw the diagram on your pen, on your copy, and just try to calculate the final answer. So please read the question very carefully first. So for this question you have 5 minutes, because this is very important. Such type of question you will get, you will expect in the your final exam, in the 3 marks or 5 marks or 4 marks, or in the gate questions or another competitive exam. Generally in the gate type of question, because here the calculator is available, so you can expect such type of questions also. So please just try to calculate. You have 5 minutes. So let us discuss. So you have the gamma w is 9.879, so it is nothing but your rho into z. Okay, flow with flow rate, you have discharge value is 0.3 meter cube per second, and you have one pipe A and B with the length is 10 meter, uniform cross section. That is, the cross section is very uniform throughout the length. Okay, the end B is above, and end A is, okay, end B is above end A. Okay, so like that, or you can draw, this is your end B which is above and end A. Okay, and pipe make the angle 30 degree with the horizontal. So this is your horizontal and angle is 30 degree. Okay, fine. The pressure of 12 kilonewton meter square at B. Here is the pressure B is given 12 kilonewton per meter square, and you need to calculate pressure at A in the same unit. So you know one thing, the uniform cross section. Uniform cross section means Q A is equal to QB as per the continuity. So area will be constant. Area will be constant at A and B. So means area if constant, then velocity at A and velocity at B will be the equal. So here VA and VB. So such type of, so the pressure calculation, for this you need the energy balance, means energy at A is equal to energy at B, and this is the energy at B and energy at A you can calculate using this Bernoulli's equation, P by rho z plus V square by 2z plus Z. So this is about A, and now P by rho z plus V square by 2z plus Z. This is B. So you know one thing, the velocity at A and B is equal, so these will be the equal and will be the plus minus cancel out. Now at ZA, ZA is 0, but how much ZB? So this is the your ZB, but how much? So the length is given of the pipe is length 10. If this is 10 meter, then you have, this is 30 degree, this is 10 meter. So how much? This one. So you know the sine theta is equal to this one, if this is ZB by 10. So ZB is equal to 10 into sine 30. Sine 30 is nothing but half, so you will get 5. So ZB is equal to 5. Pressure already you know. This is your pressure is given 12. Rho Z already given 9.81, 9.879, and here also 9.879. So you know everything. Here is a 5. So final PV is equal to what? PV by 9.879 9 and this side is 5 is already, and PA side is 12 divided by 9.879 and plus 0 plus 0, or you cannot try. Let me just erase. So you can calculate PB very easily. 12 divided by, if I consider 10, let us consider 10 minus 5, so your PB is equal to, this is 1.2 minus 5, so you will get how much? This is 4.3.8 minus 3.8, remember, and your PB is equal to, if this is 10, so this is 38. Somewhere we are doing mistake. Let us see where. But these are the process. Somewhere in the calculation mistake we are doing, but these are the how you will proceed. So I have the final solution. So don't worry. Because of the velocity is same, so that's why we'll focus on the piezometric head. P by, that is the pressure by rho z, and rho z means here is the gamma w is given. So your PA is equal to, oh sorry, I think the pressure for the, okay, for the pressure B ind we have the pressure. So here it mistake. Where is the mistake? Now I got it. Because in the question PA is given, not PB. Remember, PB is given here, and you need to calculate the PA. So PA you need to calculate divided by 10. I am considering the 10, and here PB is given 12 divided by your 10 plus 5. So 1.2 plus 5, that is 6.2, and PA by 10 is equal to 6.2, which is your PA is 62 kilonewton per meter square. So yes, you can go with this. Option D will be correct. Okay, so please remember everything. So now let us discuss question number 14. The head loss coefficient in a sudden expansion shown in the figure below, this is the figure, is proportional to the head loss coefficient. Whatever we have discussed earlier, your v square by 2z and some coefficient is there. So for the calculation of this coefficient, this is proportional to, for such type of system, such type of pipe system, the proportional to which option, whether d square by capital D square, 1 minus small d square by capital D square, so like that. So this is also calculation you need to calculate. So another you have for next this question you have 5 minutes. So please just think on that and try to write your answer. Okay, let me discuss. So here is, you need to calculate the coefficient of the sudden expansion. So due to the sudden expansion you have head loss v1 square minus v2 square divided by 2z. This is your head loss formula. But so here is question is asking about your k. So when we will get the this k factor, let us something here is k, and you will represent the this whole thing in terms of v1. So how you will, from this form to this form, how you will switch? So for that, you know one thing, what the discharge here will be is equal to discharge here, that is a1 v1 is equal to a2 v2. So a1 is what, pi by 4 into d square v1, pi by 4 into capital D square v2. So pi by 4 will be cancel out. So v2 will be small d square divided by capital D square v1. So we'll put the here in this equation the value of v2. So your HL is equal to v1, because you need to write the expression in terms of v1, that is velocity in this pipe, minus v2 is d square divided by capital D square v1 whole square, okay, divided by 2z. So now I want to take the common, v square I want to take common. So once you will take the common, 1 minus d square divided by d square okay. So v square I have taken from here, v1 square, and also from here, yes, and 2z is here, and this final expression will be the k. So your final expression will here, k will be 1 minus d square by d square, this will be the final. So option C will be correct here, 1 minus d square by capital D square, not option C, because this is the whole. Yes, option C you can go, this will be here like that, not here. So option, you will go through the option C. So here is the step by step calculation, okay. Oh, no, sorry, the formula is for this HL is v1 minus v2 whole square by 2z. So remember please, such type of mistake you can also do. So v1 by, so everything is same, so this is whole, not like that, this is whole power. So here is the power is like that, and after that you will get the whole power. Here is 2 and v1 square we have taken the common. So yes, now it is correct, option C will be correct. So remember please, you can also you can do such type of mistake in the final exam, so always remember the head loss will be like that. So you can think here I have written not, Okay, I was telling HL is equal to V1 square minus V2 square by 2Z. Once you will do the dimensional analysis, you will get the same dimension with this. So I was telling, I was thinking like that, but not. So remember please, this will be the formula. Okay, now let us move with the next question. The rate of flow of water through a horizontal pipe is 0.25 meter cube per second. The rate of flow of water, horizontal pipe is given. The diameter of the pipe, which is 200 mm, is suddenly enlarged. The previous link to the previous question to 400 mm. That is, here is was 200 to 400 suddenly enlarged. Okay. Determine the loss of head due to sudden enlargement. So please just try to calculate using this equation. So you need to calculate the head loss due to the sudden enlargement. So again you have, here you need to calculate the area at point 1, point 2, that is the in the smallest diameter, capital, and then the enlarged diameter, and then you need to calculate the head loss. So head loss is nothing but, okay, first you try to calculate, then I'll show you. So please just try to calculate. Okay, let me just calculate. So diameter is given, the same, you can draw the diagram same, similar to the previous question. So here is diameter is 400, that is 0.4 meter, and here is 200 mm, that is 0.2 meter. Okay, and discharge you have 0.25. So for head loss, you know the formula, sudden enlargement K V1 square by 2Z. So you need to calculate K. So what is K? 1 minus D square, small d square means 0.2 square divided by 0.4 square to whole square, 1 minus 0.04, 0.16 whole square. So you will get 0.16 minus 0.04 divided by 0.16, to whole square. So it will finally, the k value will be 0.11 by 0.16 whole square. So you can remove this one. So let me just calculate k value. 11 divided by 16 square, 0.47, k value 0.47. Okay, what is v1? So v1 is nothing but discharge is equal to a1 into v1. So a will be pi by 4 into d square into v1, and 0.25 is already given. So v1 is 0.25 into 4 divided by pi into 0.2 square. So v1 will be, let me just calculate. So your, okay, here you can write very clearly. So this is your 100, so this will be the 1, and here is pi into 0.04. So what will be the pi into 0. So 1 divided by 0.125. This is 8. Okay, so your 0.47 into 8 square divided by 2 into, we can take the 10 for the easy calculation, and we can consider this is 0.5 just for the easy calculation. 0.5, so this will be the 20, and 64 into your 0.5 divided by 20. So this is your 32 divided by 20. This is, once you will calculate, this will be 1.6, means near to the 1.6. So we can say the 1.8 may be the correct, if the calculation is correct throughout. Yes, 1.816 will be the correct answer. So hopefully you already understand. So how you will calculate this type of loss, the sudden enlargement loss. Okay, so next question is, the Prandtl mixing length in the pipe flow is constant, 0 at the pipe wall, a function of shear stress at the wall, a function of Reynolds number. The Prandtl mixing length is the function of what? So that is the function of shear stress at the wall, function of Reynolds number, 0 at the pipe wall, constant. Just think on that, please. Okay, this is little bit difficult question, so just I will go through the answer. So here is about the Prandtl mixing length. What is Prandtl mixing length? actually, let me just go through one by one very precisely. So in turbulent flow, actually in the turbulent flow, the fluid motion is irregular and dominated by the eddies. Eddies means this such type of fluid motion, unlike the laminar flow. Because in the laminar flow, basically the viscosity is dominated, but in the turbulence flow, mixing happening. So what happening, to model this means, to understand the mixing phenomena, what the Prandtls do, the mixing length hypothesis. And in the mixing length hypothesis, the Prandtl assumed that the fluid particle moving in turbulence carrying its momentum for a short distance. Means once the fluid is moving like that, means the fluid particle carrying momentum over the short distance, maybe the vertical or in the horizontal direction, and this distance is called the mixing length. Means let us suppose a particle moving here to here, but from here to here the particle is moving and with having some momentum. Momentum means the velocity changes from here to here, because here is the velocity is, let us suppose, 1. If the something is moving upward direction, definitely the velocity will be the more. So let us suppose here is the velocity is high, that is 1.2. So momentum means what? The change in the velocity. So this distance will known as the mixing length, and this is calculated by using the, as you know, in the turbulent flow is like that. If this is time, if this is velocity, so turbulent flow is like that. This is the reference line I have considered. So turbulent flow is like that. So when we will average, maybe the average line will be shifted towards the maximum fluctuations. So here we have shift, let us suppose here shifted. So this is your u average, and then these are the fluctuations from this line to the fluctuation, similarly in the downward direction. So this is the fluctuation. So the based on the Prandtl model, these fluctuation you can calculate using the mixing length and the gradient of your velocity. So this was the concept behind the mixing length, and it is thus from here you can calculate very easily Reynolds shear stress very easily using. And why the Prandtl mixing length important? Because first I want to show you why it is important. Because in the fluid flow, that is in the Navier-Stokes equation, in the Navier-Stokes equation we have this is the Navier-Stokes equation. So for solving the completely Navier-Stokes equation, because we can the mathematically the still there is no no one solved the completely this Reynolds shear stress for the complex problem. So for that, what the Reynolds decompose these velocities in two component, average is instantaneous, and after the calculation he come up with this u dash, and that is I means u dash in the another direction, velocity in another direction, that is I direction. Or you can say if I is corresponding to x and j is corresponding to y, so velocity in x direction, velocity fluctuation. So for modeling of this, how, because you don't know how much this, so for modeling of this there is a lot of assumptions, lot of model developed, these are the models. But the Prandtl model also you can calculate, that is the fluctuation in x component, fluctuation in y component, you can model using the Prandtl also. So this was the main reason. So here you can see there is u dash and v dash, u dash and v dash you can very easily calculate if you know the mixing length. So these were the concept behind your the mixing length. Okay. So okay, so now coming on the your question. So mixing length actually in the turbulent flow near the pipe wall is K into Y. Mixing length is calculated by the K into Y. So what is K? K is the one Karman constant which is 0.4, but near the wall your Y will be 0. If Y will be 0, your mixing length will be 0. So yes, you can go through this option. Near 0 at the pipe wall, because your Lm is equal to K into Y. If it is K into Y, then what will, if the Y will be 0, because 0 at the pipe wall, definitely Y distance is 0 at the wall, so Lm will be the 0. So this is correct. This is not a function of shear stress, not Reynolds, the function of one, this is Y and one common. So this was the some basic understanding. Now coming on the next question. In fully rough turbulent pipe flow, the friction factor is a function of Reynolds number, and the this is the diameter, d is the diameter, and es, so, and a function of es, the epsilon s divided by d, and a function of Reynolds number, and independent of Reynolds number, and the your es by d, that is the relative, you can say the relative diameter. So in the turbulent flow actually, fully rough turbulent flow. So again, this is very important question. So here is your friction factor, on this axis your epsilon es by t, and here is your Reynolds number, and this is the region of laminar, this is the region of your transition, then after fully developed flow, and then after this is fully developed flow, this is fully rough flow, rough turbulent flow. So in the rough turbulent flow, basically your is varying like that, very constant, means it's depend on your this only. Option B will be correct here. So this is a Moody's diagram, remember please. So in turbulent flow, actually we calculate the friction factor using Moody's diagram, and some another formulas also there. And in Reynolds in the laminar flow, we calculate the friction factor 64 divided by Reynolds number. So in laminar case, it depend on the Reynolds number, but in the fully turbulent, fully rough flow, turbulent rough flow, it's depend on the relative diameter. So here is given already everything. Option B is correct. The explanation is also given. So question 3 is the head loss in 100-meter length and 0.1 meter. This is the last question for today. And 1 meter in diameter of the pipe, and friction factor is 0.02. Carrying water is 10 meter. Okay. What is this? Let me just read. The head loss in 100-meter length of a 0.1 diameter pipe having the friction factor. Okay, head loss is given 10. The boundary shear stress is in kilopascal. So you need to calculate the boundary shear stress. If the head loss is given 10 meter, length of the pipe is given 100 meter, diameter is given 0.1 meter, friction factor is given 0.02. So boundary shear stress, how we will calculate? So here is the calculation is given already. So the boundary shear stress you can calculate using this formula. Tau wall HF rho ZD by 4L. This is the your headless formula. So from here you can calculate very easily. So your final answer will be the 0.025, 0.0425. This will be the final answer, option B. So hopefully you have got it, the concept of pipe flow and the questions also. So we will again meet in the next session. So thank you for attending the session today.
Thank you, sir.
Okay, thank you. Okay, you can leave.